Good morning, everyone. I'm Galih, a postgraduate student from Universitas Indonesia, intending to present my research entitled Effectiveness of Damping Device Uncoupling Beam of 50-story Building Based on Nonlinear Analysis Procedure. My outline is as follows. The first is introduction, the second is literature review, the third is research method, and the fourth is result and conclusion. The question is why am I interested in this research? Based on SCA 318, the coupling beam with the high shear force should use diagonal reinforcement, but the coupling beam with diagonal reinforcement is difficult in construction and retrofitting. For the reason, this research is looking for a solution by replacing the coupling beam with a damping device. The next slide is literature review. According to Nonlinear, coupling beam with a length per head ratio less than 2 and a shear ratio greater than or equal to 4 must use diagonal reinforcement. And for length per head ratio between 2 and 4, you can use regular or diagonal longitudinal reinforcement, but it is recommended to use a diagonal because it is more stable. Actually, research on VCD and RFD has been done. In 2000, the use of new friction damper emerged when the friction damper did not use slotted tab like the previous friction damper, but instead used a rotating shaft which was called a rotational friction damper, the result of which shows that the damper component produces a stable hysteresis curve and the ease of replacing the damper when it is plastic. The use of viscoelastic damper on coupling beam element also shows good results regarding beam ductility compared to the conventional coupling beam and provides damping in all lateral vibration modes. Damping device consists of displacement-dependent device and velocity-dependent device. For example, friction damper for displacement-dependent device, fluid and solid viscoelastic damper for velocity-dependent device, and we can see idealization of dissipation device response in the picture. The next slide is research method. In the slide, show about the building data that I use for modeling. This is a typical floor plan where the overall function is an office building. It can be seen in the table of the strength of the material used and the position of the coupling beam as shown in the picture. We can see in the table, column used 35 MPa for concrete strength, shear wall used 35 too, like a column, and coupling beam used 35 MPa for concrete too. Beam and slab use 30 MPa for concrete. The strength of steel material use 420 MPa. The dimension of column have the difference in every 5 floors. We can see the differences from this table, and the thickness of the shear wall use 400 millimeter, and the coupling beam dimension with height 1.6 meter and length 5.5 meter. And this building I use dual system lateral resisting with special moment frames, column and beams, and special concrete wall. And the office building consists of typical plan and roof loading with superimposed dead. In the typical plan, superimposed dead load 1.5 kilonewton per meter square and live load 2.4 kilonewton per meter square. Roof MA superimposed dead load used 2 kilonewton per meter persegi per meter square and live load 4.79 kilonewton per meter square. This loading based on Indonesian code. The following is a modeling plan consisting of 5 models. The first model using rotational friction damper on all floors. The second model on floors 5 to 9. The third model using viscoelastic damper on all floors. And the last model with viscoelastic damper on floors 5 to 9. And the image shown is an overview of the VCD and RFD that will be used. And the next slide is about the analysis method. Modeling analysis consists of two stages. The first is linear analysis using earthquake DBA or design-based earthquake equal to third MCER based on ASCE 7 using a TAPS 3D program to obtain reinforcement detail for nonlinear analysis. The second is nonlinear analysis, modeling the nonlinearity of component using 11 pairs of ground motion using the Perform 3D program, and the result must not exceed the CV limit or collapse prevention limit based on ASCE 41. This is an example of nonlinear modeling by modeling backbone curve as specified in ASCE 41, and also how to model FCD using the GMM, Generalized Maxwell Model, and RFD modeling using Sirhoe's with properties obtained from the damper supplier. Next, we will discuss upon the result obtained. The first result is about the storage share. There is an increase and decrease in the storage share of each model, where the most significant increase, maximum plus minus 18%, and decrease maximum plus minus 15% are in the y direction, in the direction of the damper in the RFD model. In the y direction, there is decrease in overall story. The next result is about story drift. There is an increase in story drift on some floors, but still below the 4% limit. The decrease that occurs is mostly on the y-axis when the damper is installed. The next is a result about component action. In the first component is shear wall. There is an increase in the strength of concrete and steel, but the increase is not too significant and is still far from the CV limit. We can see in this picture the position where increase and decrease from this table. The next component is column. For the column element, there is only a slight change. The majority of the results have not changed compared to the model without the damper. Column performance show is still below CP. We can look at the table from model with viscous elastic damper at the below floors getting increased compare the rotational friction damper. But overall results show that no change from compared with the model without a damper. The next component is beams. In the beams element, there is also an increase in the performance of the beam. The difference between the increase in the viscoelastic damper and rotational friction damper model is that the increase in FVCD occurs on the lower and upper floor, while in the RFD, the increase occurs on the middle floors. However, all beam performance is still below the GV level. We can we can we can look at the table that happened in the FCD with the red colors in the upper and below floors, but in the RFD almost in the middle floors. The last slide is conclusion. The conclusion of this research are model using damper, both viscoelastic damper and rotational friction damper have decreased and increased global and local performance. However, the increase that occurs is still below the limit for the building model. Because of this, the use of damper element on all floors or on floor 5 to 9 can make a solution related to the difficulty and installing diagonal coupling beam reinforcement by replacing it with the damper element. Furthermore, if there is damage to the damper element after the earthquake happened, it can be done easily without a long repair time when using conventional coupling beam. This is my reference that I use. And thank you very much.